Okay, so we have 1.3 compositions of linear functions. And you have two objectives: to perform compositions with 2 to 3 functions, and to verify if 2 linear functions are inverses by composition. Before we do that, we're going to work in a little bit of review. So you're going to see a lot of fractions with composition functions, so I wanted to kind of go over multiplying with them a little bit. All right. When you see multiplying fractions, you really are multiplying across for both the numerator and the denominator, but sometimes you don't see that. Sometimes you have to put the 1 there so we have the other number, right? This is not 1 times 2 and 2 times 2. This is 1 times 2 and 2 times 1, which gives you 2 over 2, which is then division, right? Which brings you back to 1. Now, if you really know your fractions well, you'll be able to look for those cross patterns where we have a number like this, 2 over 2. Crossways, which we can always cancel out to be 1 a little bit faster, which you can see in this next one. 9 over 2 times 2, we put it over 1, but we see that 2 across, 2 over 2 to be 1, which now, this is 9 times 1, this is 9 over 1, or just 9. Okay, so if you find those cross numbers, we can simplify. Look, 5 over 5, that's 1. 2 over 2, that's 1. 1 times 1 is 1. Okay, and if you want to get into why this really works, if you think about it, 2 times 5 is the same thing as 5 times 2, right? So if I see a 2 over 5 times a 5 over 2, well, I could flip this, right? I could write that same exact thing as 5 over 5 times 2 over 2, and then I have the same number over the same number. We're just doing that faster by looking at the numbers that go across. But if you don't see those cross numbers, if you just have something, which I'm going to write in blue up top, a 3 over 4 times a 2 over 5, then you just go right across. 3 times 2 is 6. 4 times 5 is 20. And then we ask ourselves, can we simplify? Which this one we can. And we look for the biggest number that can go into both of them. I see a 3 can go into a 6, but a 3 can't go into 20, right? So that can't be our number. But a 2 can go into both. A 2 can go into 6 3 times. 2 can go into 20, 10. So I get a 3 over 10. And we won't be able to simplify any further there without making a decimal, okay? All right, our next thing is compositions, right? What are they? And it is applying one function to the results of another. And we have this little example here, all right? The way we read this composition is f of g of x, all right? And we can also, you can see this arrow pointing to the right, write it, and it makes a little bit more sense when you write it this way over here, right? This f of g of x. What we're saying is you're going to take that x value and you plug it into the g function, and you're going to get a number out of that g function. Whatever number you get out of that g function, you then plug into the f function, okay? And you kind of start with the number that's closest to the x. So if I look at this left one over here, I see that g is closest to x. So I'm going to take, you just read, x into g, and then whatever output of that is goes into f. So if I want to take this exact example of f of g of x with these two functions down here, I'm going to take this function and plug it in for the inputs over here. So this would be not f of x anymore. This would be f of g of x, which would be 3 times all of what g of x was, negative x plus 2, and then finishing the f function to have minus 1. And then I need to simplify. Take the 3 in. 3 times negative x is equal to negative 3x. 3 times 2 is 6, minus 1. So I simplify, I get negative 3x plus 5. And this is, which I could write it either way, but you could see it like this. F of g of x equals negative 3x plus 5. I've created a new function here using compositions, right? But I'm really just taking, whatever I would have plugged into g of x and putting it into f of x also. So let's do some more examples. You're going to see it in many different ways, right? You're going to see it here where we're telling you to plug in an x. You're going to see it here where we have multiple compositions. And then you're going to see it like this also where there's just 2. But sometimes it can get pretty difficult or pretty lengthy. Okay, so let's jump into g of f of 5. Okay, so we're going to take, let me use my pointer, this 5 value, plug it into f. So we look up for the f function, that's 2x. So I'm going to take 5 into that. So f of 5 equals 2 times 5, which we know would be f of 5 equals 10. I'm now going to take that 10, that was the output of f, I'm going to plug it into the g function. So we have g of 10 equals 3 times 10 plus 5. You end up with 35. Okay, but I need to write that as my composition, right? So g of f of 5 equaled 35. This looked very different from the last one, right? The last one, we didn't actually know an input value. So we took the function and plugged it in so that whenever we get the input, we don't have to go to multiple functions. We've like created a new expression for that composition. If you already have the number, you don't have to do that. You can just jump into plugging it in the order that it needs to. Just always remember that we're going to take the closest one first, okay? It like follows from right to left. 5 into f, whatever comes out of that goes into g. Okay, let me do that. Now with the triple, it's the same thing. Okay, let me make some erases here. Except for we're going to do this multiple times. All right, we don't actually have an x value, so we're just going to take h of x, right, and plug it into g, and then whatever we get out of that, we'll plug into f. So this is going to be a pretty long one. So h of x is equal to x over 2 minus 1. I'm going to take that and go into g. So I'm just going to start with that. So g of h of x equals 3 times x over 2 minus 1 plus 5. I use the distributive property, right? I go in to both of them, and I should get 3x over 2 minus 3 plus 5. I need to simplify, and I'm going to get, and I'm just going to actually write this as 3 over 2x plus 2, okay? Now, I've gotten that output, and I need to take that and plug that into f of x, which is just 2x. So this is going to be f of g of h of x, that's really long, equals 2 times 3 over 2 x plus 2. And then I use that distributive property. So 2 times 3 over 2, 2 times 2 gives us, and we see the cross, right? Let me zoom in here, right? This would have been under 1. We see that cross cancel, that 2 over 2, right? So we should just end up with a 3 over 1. Zoom back out. Or just a 3x, and then 2 times 2 is 4. So I'm going to write it the other way. F of g of h of x equals 3x plus 4. That was a long one. Whoa. Okay. And then finally, you can have those compositions with just 2. We have h of g. So now we're taking g and plugging it into h, okay? Which I know in this last one, we technically did g of h, so this is the opposite, h of g. So I'm going to take h of g of x, like that, is equal to 3x plus 5 over 2 minus 1, all right? And you can see here, right, all this 3x plus 5 came from the g function, and I plugged it in for the x in the h function, okay? And then I do need to simplify this, right? But we end up with the 3x plus 5 over 2 minus a 1. That looks kind of tricky, okay? And so back to our fractions, right? We could put this over 1, but it's not as easy as multiplication. With multiplication, you can just go across and multiply, right? But this is subtraction. We need that denominator to be the same number as the other one in order to subtract. Luckily, we know that this one is under 2. And if we're subtracting by 1 over 1, well, then I can just multiply the top and bottom by 2 to get the same denominator, so minus 2 over 2. Now, if that confused you, think about this. 2 over 2 is 1. Well, excuse me, negative 2 over 2 is negative 1. Negative 1 over 1 is negative 1. I haven't changed the value, I've just changed what they look like. So then I have 3x plus 5. And now I can actually do the subtraction. I can go a little bit further and write this. I'm going to write it all under a single 2 now. 3x plus 5 minus 2. So I can simplify that 5 minus 2. And I'm going to get h of g of x equals 3x plus 3 over 2. Now that's one of the more difficult ones, but you are going to see fractions, okay? And you're going to need to feel a little comfortable with them, so really try to understand that one and make sure you ask questions if you need help. Okay. So I'm going to ask you guys now to pause it and give these two a try, kind of build that comfort with compositions. Okay, whoops, skipping around here. All right, so the other thing is, how do we verify inverses using compositions? So the previous video was all about inverses, right? And we can use compositions to tell if these two functions are inverses. And the way that we do that is we'll do two compositions. We'll do f of g of x, and we'll do g of f of x. So we're basically doing a composition with both in each order. And in order for these to be compositions, when we simplify, I should get an x. That's what I should get for both of them. Okay, once I've fully simplified, if they're inverses. If they're not inverses, then I, will get different things, and I won't get x each. So let's try the first composition, which is taking the g and plugging it into the f. So I'm going to have f of g of x equals, and my x is all the way up here, right? And so that looks a little tricky, but we can do that, right? That becomes a 2x minus 1. I'm putting parentheses around it because that's where x was. Plus 1 over 2, okay? I'm going to take away those parentheses. I have a minus 1 and a plus 1. Those are going to cancel out. So I get 2x over 2. 2 divided by 2 is just 1, and I'm left with x. So far, so good, okay? But we need to make sure the other one also gives us that, okay? So I'll write that here. So I'm taking f of x, now I'm plugging in g of x, right? So g of f of x. I know I'm rewriting it again, but it just gets me more comfortable, should get you more comfortable with compositions and plugging a function into another function. So I should now have 2 times all of the f function, like that, minus 1. So now I'm going to have to do the distributive property, okay? And this is going to look like a lot, but remember, this is, wow, that's a tough distributive property. Still 2 over 1, right? We have a fraction in there, okay? So when I distribute this, I distribute the top, the 2 to the x plus 1, and the 1 to the 2. So I end up with 2 times x plus 1 over 1 times 2. And the only reason why I wrote it like that is so that you can see how I multiplied that into the top and to the bottom. And then I'll have to distribute here because of those parentheses. And there's still that minus 1 at the end, which this is the error I see most people make, is they forget to write that end piece because they're so focused on those distributions and compositions. So I end up with 2x plus 2 over 2 minus 1. Which again, this looks pretty difficult, but we can separate this, right? I'm separating this part here, the 2x plus 2. I'm going to write it as 2x over 2 plus 2 over 2. Like this. Okay, and now I'm able to start doing things. 2 over 2 cancels, I'm left with x, right? 2 over 2 is 1 minus 1. Those cancel. I'm left with x. So I get to finally write and say, yes, they are inverses. So this one was a little tougher, right? Especially when you're plugging them in both ways, you run into some more difficult distributions, right? You run into some more lengthy problems. Be patient, take your time, and you'll have to try and uniquely use your algebra skills to manipulate those expressions around so that you can simplify all the way down to x. Not all of them will be this tough, but I figured it'd be better to show you a more difficult example so that you were ready. Okay, so now you're given one right here, all right? And I want you guys to give it a try and see what you get. All right, word problems, okay? So this one is how do we see those compositions in our actual problems? So the cost in dollars of producing n sneakers in a factory is given by C of n is equal to 60n plus 750, and the number of sneakers produced in t hours is given by n of t equals 50t. So you can see we're given two functions, right? Two functions that mean different things, but they're very similar, right? And we say write a function that represents the cost of sneakers as a function of t hours, okay? So think about that. Which function, has your time as your input, and which function is dealing with cost? Okay, so I'm going to write these over here. So we have C of n equals 60n plus 750. Here, the input is n, which is sneakers. Okay. And then you have your output, which is cost. Okay. Your other function, n of t equals 50t. Okay. You have your input is time. Okay. And your output is your numbers of sneakers produced, right? So number of sneakers. Okay. So if a composition, we take the output of a different function and plug it into something else, you can kind of see this link here. Look, the output, here we go. The output is linked to the input there. They both have to do with the number of sneakers, okay? So I'm gonna write this as not C of n, I'm gonna write it as C of n of t, okay? Because that allows me to take time into my sneakers function here that tells me how much I'm gonna make, or how many sneakers I'm gonna make. And then I use that as the input for the C function. So C of n of t is going to be equal to 60 times 50t plus 750. Sorry, I know I'm getting off the edge there. And then I'm going to simplify, so I'm going to get C of n of t is equal to, what, that's 3,000? Yeah, because 2 zeros, and then you get another one, 3,000t plus 750. And so that would be my new function, okay? All right, now find C of n of 5 and explain what this number means, okay? So we made our function, right? And now we want to plug 5 into it, so we're going to get 3,000 times 5 plus 750, and we simplify, right? 3,000 times 5 gives us 15,000 plus 750. We simplify again, we get 15,750. Okay. Explain what this number... Okay. Try that again. Explain what this number represents. Okay. We took a number 5, which was hours, right? We plugged it into the n function and got out how many sneakers we were going to make in 5 hours. We took how many sneakers we were going to make, we plugged it into the C function that tells us how much... when I say how many sneakers we make, plug into the C function, which tells us how much money we're going to make, right? So we're going to simplify that. We're going to say we figured out how much money we're going to make selling sneakers if we make 5 hours worth of sneakers, okay? Which the answer to that would be $15,750. Okay. Now you guys have a word problem. I want you to pause and give this a try, but be very careful here because if you expand, it'll become a very difficult problem. So I do not want you to expand that expression. I just want you to plug it in and don't expand the cube, okay? And you'll see what I mean when you try the problem. All right, that's it. Stay tuned to the end of the video. I'm going to ask for feedback on this one, and then I'll see you guys in class.